Hi everyone, my name is Neha Kardam, and in this lecture we are going to learn about using logic gates. So this is the preview of the lecture. We'll be covering logic circuit from a Boolean expression, minterm, maxterm, Boolean expression from a truth table from a Boolean expression, simplifying Boolean expressions, Karnaugh mapping, NAND logic, data selectors and their use, solving logic problems with data selectors. Now let's first start with the tools of the trade for solving the logic problems. So we're going to see some combinational logic circuits, the basic ones which we'll be using to deduce the or you can say the solve the Boolean expression and then form the combinational logic circuits. So some of the basic logic gates are these. So this is your and or pattern of gates, and then next one is or and pattern of gates. So mostly if you have been given a Boolean expression and you are asked to create a combinational logic circuits, so you will be using these type of pattern using and or gate. You can use other gates also like NAND gates, but these are some of the basic gates you will start with. So let's see next logic circuit from Boolean expression. So we have an example here. Draw the and or logic diagram for the Boolean expression. So right now you can see this is the expression we have, and we want to draw a combinational logic circuit based on this Boolean expression. So if you notice this Boolean expression, you see that there are four inputs. So A, B, C, D. These are the four inputs, and then Y is the output. But if you notice here, between these two and these CD, A, B, and CD inputs, we have a plus sign here. So if you go back to the basic logic gates, for example, and or not logic gate. So if you remember, like if two inputs are going into the gate and then at the output you have like something like A plus B. So in what type of logic gate you had that plus expression? So if you look back and you see that if you see, then you'll get to know that this plus sign came in OR gate. So which means the main gate is your OR gate. Okay, and then this will be taken as one input. You can take it as x1, and you can take this one as x2. Okay, so you have x1, AB is equals to x1, CD is equals to x2. So x1 plus x2 is equals to y. So we have like an AND gate which has two inputs, x1 and x2, and y is the output. So let's see next. So you see here, this is the OR gate, and in the OR gate you have two inputs, AB going in, CD going in, and we took this as x1, AB as x1, and CD as x2. So if you combine those, you will get at the output AB plus CD, or x1 plus x2. Okay. Now, how these AB and CD inputs are coming? So again, if you go back to the basic logic gates, you'll get to know there is a gate called AND gate, and in AND gate, if you send two inputs, then at the output it will multiply those inputs. All right. So what we are going to do, which means that we can put here AND gate. Okay, and that AND gate will have two inputs, A and B, right? And the output is going to be this AB, the multiplication of those two inputs. So let's see next. So that's what happened here. We have this AND gate which has two inputs, A and B, and which is going in here and then to the OR gate. And then now we have the CD. So we are going to do the same thing which we did here. We're going to put an AND gate which will have two inputs, C and D, and then CD is going to be the output coming out of from the AND gate. So you see here we have two AND gates and OR gates, and you see that the basic logic gates have been used to solve this Boolean expression. So here the key takeaways are that you should make sure that what is the main logic gate we should be using. So for example, in this case, the main logic gate was the OR gate, right? So you first see the big picture, what is going to be the main gate, and then start backwards, seeing like what are the gates needed to get into. So you saw that we started with the OR gate, and then we went to the other inputs and made the AND gates. So this expression is similar to what we have made here, this combination logic circuit. Now let's see next. So we're going to do a test. Draw the OR AND logic diagram for the Boolean expression. So we have this expression here, A plus B dot, and then C plus D is equals to Y. So the first thing, if you want to solve the Boolean expression and make the combination logic circuit, the first thing you will see is the big picture. So big picture is that this is kind of one input, this is kind of a second input, and they both are being multiplied, right? So when they are multiplied, which means what type of logic gate we'll be using? We will be using, in that case, AND gate, right? So this is going to act as one input, and this is going to act as another input to the AND gate, and the output to the AND gate is going to be this Y. So see, step one, this is what you do. AND gate, make an AND gate, and then put two inputs. So A plus B is going to be one input, C plus D is going to be second input, and the Y is the output. Now the second step is to find what is A plus B. A plus B, you know, that is an OR gate. So that's what we have made over here, OR gate. And then in OR gate, these two inputs are going A and B. Okay, so A is going into the OR gate, B is going into the OR gate, and in OR gate we already know that the output of the OR gate is the sum of two inputs going in. Okay, so we have A plus C, B here, and then if you see this one, we have C plus D. So we can do the same thing which we did here. So let's do that. And then by doing that, we have like two OR gates. These are the two OR gates, and two inputs are going, A and B, C and D, and then at the output we have here A plus B, and here we have C plus D, and these two inputs are going to an AND gate, and from AND gate we have this output A plus B multiplied with C plus D. Okay, so now see next, Boolean expression. So we're going to see sum of products form, which is also called minterm form. And in this minterm form, you can see this is one of the example is given. For example, this is just an example. For example, if you have A complement dot B plus C dot D complement is equals to Y. So complement, I hope you remember from our previous lecture. So for example, if A is 0, then the complement of A is going to be 1. And same here, if D is 1, and then the complement of D is going to be 0. Okay, so this is a form given, and if you notice this form, then this is the same thing, right? Here, sum of products. So there is a sum here, sum of products. So this is the product. Okay, so these are the two products and they are being summed here. Okay, so this type of expression is your sum of products, and this type of form is called your minterm form. So both are these are the two names, minterm form, or you can say sum of product forms. And next we have another form which is called product of sum. So as its name suggests, product of sum. So this is a product, you see a dot here, product of sum. So this is the sum, a plus b bar, and then c bar or c complement plus d. So this is the sum, and we are taking the product of these sums. So that's why we say product of sums form. Okay. And another name for this type of form is called your max term form. So anytime if you see like max term form, just make sure that it's the same thing, which is product of sum. And if you see min term form, just make sure it is sum of products. And in some of the cases, you might see that there is a short form which is used. So for example, for some of products, people use SOP, S-O-P, SOP. And for product of sum, they use like POS, P-O-S, POS. All right, now see how they are useful. So let's see here. We are going to write the Boolean expression that describes the logic in this truth table. All right, so we have this truth table, and this is for 3 variables. You can see A, B, and C are my inputs, and which means these are of 3 variables, and these are the input different combination we can have. So 4 zeros, and then 4 ones, and then 2 zeros, 2 1, 2 zeros, 2 1, and then 0 1, 0 1, 0 1, and so on. So this is the combination we can have, and then you may have like more inputs. So this is like a basic example. You may have like more than 3, like maybe 4 or maybe more than that. All right, so corresponding to right now for this particular example, for these 3 inputs, we have an output generated over here, and this is the output corresponding to this input. Now let's see how we are going to form the Boolean expression from the truth table. So we already have the truth table, and then how we are going to form the Boolean expression. So previously what we did, we already had the Boolean expression, and from the Boolean expression we were trying to make the combinational logic circuit. Right now here is we have to make a Boolean expression out of truth table. Okay, so let's see what are the steps. So the first step is to focus only on the truth table lines without outputs of 1. Okay, so we have to do what? Focus only on the truth table lines with outputs of 1s. Where are the outputs of 1s? We see here there are only 2 places where the output is 1. So for this place, when A is 0, B is 1, C is 0, and the second time when output is 1 is at that time your ABC, they are all 1, right? So let's see. So now the second step is AND the inputs of these 2 lines and logically OR the AND groups. Okay. So what we did, so for example, here we had 1. Okay. So if we look here, so we have 0 here. So whenever you have like 0, you will complement that input. So for this particular instance, here we have 0 1 0. So this A is complement. Okay, that's why you see here A complement, and then multiplied with B, and B is 1, so this is not going to be complemented. This will stay like this, B. And C is complemented, so that's why you see here complemented. And then again you put a plus sign here, and then you go to the other one which you have on the output. So you have 3 ones here, ABC. Okay, so these are all ones, so you will just put it like this, ABC is equals to Y. Now if you see what type of expression it is forming. So in our previous slide, we learned about sum of products, products of sum. So what do you think what it is? So if you notice, so these are the products, okay, and then these products are being summed, which means it is a sum of products, okay. So this is your min-term Boolean expression. So you can see here it's written min-term Boolean expression. Okay, so this is going to be your final Boolean expression. All right, so this was an example for sum of product. Now let's see next. So it's a test, and let's see if you are able to make the Boolean expression. So the first step, if you remember from last slide, that the first thing what we look into the truth table if we want to find the Boolean expression, we look for ones. Okay, we look for ones at the output. So here we see one here, and then we see one over here. Okay, so when this is 1, output is 1, at that time all the inputs are 0, which means we are going to have A complement, B complement, C complement, right? And let's look another one. So these are all ones. So we are going to have A, B, C. So let's see. These two outputs are 1, and this indicates this expression which we already learned, that A bar, B bar, C bar, and this is going to be same. Okay, so this is your min-term Boolean expression. So we did like 2 examples, this one and before, of a min-term Boolean expression. Now let's see next. So truth table from Boolean expression. So fill in a truth table from a min-term Boolean expression. Now this is different. So now what we have a Boolean expression given, min-term Boolean expression. So you have to make sure this is min-term Boolean expression, and that you can also get it from the type of expression it is. So you see this is a sum of product. These are the sums and these are the products. So this is the sum of products type, which means this is a min-term Boolean expression. So now the question is how we can form the output in the truth table by just looking at the min-term Boolean expression. So let's do that. Let's go one by one. If you see, this is A bar, B bar, C bar, and this is A bar, B, C. This is A, B, C bar. So at least one thing we know, that all these 3 inputs, they represent 1, right? So this is one thing. And the second thing, what we can do, we can look for where we have A bar, B bar, C bar, where we have this expression and then this. So let's see where we have A bar, B bar, C bar. So if we look here, A bar, B bar, C bar came when these 3 are 0, which means this one, right? So corresponding to this, we should have 1. And then let's look for A bar, B, C. So A bar, B, C, which means A bar is going to be 0 and B, C are 1. So we should look for 0, 1, 1, right? So 0, 1, 1 is here, right? So corresponding to this, we can put 1. And then last we have A, B, C bar, which means 1, 1, 0. So where do you have 1, 1, 0? Here, right? 1, 1, 0. So here corresponding to this, we'll have 1. Now let's see if I'm correct. So place 3 ones in output columns. So see, corresponding to that, we got all the ones. Place 5 zeros in the blanks in output columns of the truth table. So this thing I did not tell you. So now you understand, like you put all the ones and rest of the places you put all the zeros, right? So this is how you can make the truth table out of Boolean expression. Now let's see next. Truth table from Boolean expression. So fill in a truth table from a min-term Boolean expression. Now you have given this Boolean expression, and then you have to find out the truth table. So what we are going to do, we're going to look for these and this value. So A bar, B bar. So this is like unusual. This is like different than what we saw in the previous slide. Now you might think like we have like A bar, B bar means 0, 0. But if you look at the truth table, you will see you have like 2 times where this 0, 0 came, right? These are the 2 ones. These are the 2 cases where 2 times 0, 0 came for A and B, right? So which means that this is also a bar b bar and this is also a bar b bar. So it is little conflicting, right? So if you have a situation like that, what you'll do, you will put a 1 on both the places. Okay, so because they both have common, this thing is common, a bar b bar, so on both the places you will put 1. And now this is very simple, a b c, so 1 1 1. Okay, you'll look for 1 1 1 and then you will put corresponding to that 1. So once you do that, on rest of the places you will put zeros. So let's see. Place single one output column for term with 3 variables. So this slide has started with 3 variables first. So let's do that. So we have put here 1 and then place 2 ones in output column for term with 2 variables. So these are the 2 columns, term with two variables. So that's why we have 1 1, and on rest of the places you will have zeros. All right, so that's how you solve the min-term Boolean expression, and you can make a truth table out of the Boolean expression. Now let's see next. Simplifying Boolean expression. So now you pretty sure you know that you just pick all these variables and then put corresponding to that ones, right? So this one a bar b bar c bar, so that's why we have 1 here, a bar b bar c, which means 0 0 1, so you have here, and then you have a b bar c bar, which means 1 0 0, so that's why you have here, and then you have 1 1 0, so that's why you have 1 here. Now here, so what this slide is telling you is to simplify the Boolean expression. So right now what you see here is not simplified, it's really big. Okay, so what we want to simplify this expression. Okay, there are 2 ways of doing that. First is like you can use the formula. There are some Boolean algebra formulas which you can use and simplify the expression, or the other way is by looking at the truth table. Through that also we can simplify the expression. So we are going to see that second way, like by looking at the truth table and then simplifying it. So how, like if you think hard, then you will get to know that we can actually simplify this. So how we can do that? If you see these 2 ones, right? If you see these 2 ones and you see that something is common here, right? These 2 zeros and these 2 zeros are common, right? Which means if I write a bar and b bar, then I don't have to write these 2, right? And then you have here, so here you have 1 0 0, which has 1, and then you have 1 1 0, which has 1. Now if you see the common binary in these 2 cases, so this is 1 0 0 and this is 1 1 0. So you see that this one is common, and this C and this C is common. So which means like we can take this as A, okay, A for this one, and then C bar for this one, right? So our expression is going to be A C bar plus A bar B bar. So this A bar B bar is for these 2, like this is the uncommon part and then rest is the common part. And for A C bar, if you look here, this is the common part, or don't worry about like this covering here. This doesn't cover this 0. So we are just seeing only this one and this one. Okay, and rest of it is common. So this is going to be A, and since it is 0, so that's why we have C bar here. I'll just go back again. So I hope you understand this expression, A C bar plus A bar B bar is equals to Y, and how it came from the truth table. Okay, just make sure that this center one does not include that include our simplified form. Only we are right now dealing with this one and this one. Okay. Now, rule here is eliminate term within loop that contains a term and its complement. So that's what we did here. Okay. Now let's move on to another simplification way. So I forgot, like first was the you can use the formulas, and then second you can do directly from the truth table, and the third one is this is using the Karnaugh map method. It is also sometimes called K-maps. So using the K-map, it is like the expression simplifies very easily, and it's very frequently being used to simplify the Boolean expression. So right now we are dealing with 3 variables. So you can see here when I said 3 variables, these are the 3 variables A, B, and C. So if you want to make a K-map, Karnaugh map, using 3 variables, it should look something like this. Okay, you form a table like this. Okay, and then you will put exactly like this, the way it is written over here, like A bar, B bar, and then A bar, B bar, A bar, B, and then AB, and then A, B bar. Okay, so and then here C bar and C. So right now we are not going behind the signs how this has been placed and why these belongs to particular cell. For now, just understand this is the way, like how it is supposed to be done. Okay, so for 3 variables, the K-map should look like this. All these fields should look like this. Okay. Now, how we fill in all these blocks which we see here. So let's see first expression. We have A, B bar, C bar. So B bar, C bar, and then A. Okay, so we will look for this into this table. So A, B bar. So where do we have A, B bar? We have here A, B bar. And then along with that we have C bar. C bar we have here. So if we see, so somewhere here in this box, we will have A, B bar, C bar. Okay, because we have A, B bar here and then C bar here. Okay. And then we have A bar, B bar, C bar. Okay, so we have A bar, B bar, and then C bar here. So which means this block will be your 1. And then you have A bar, B bar, C. So A bar, B bar, and then C. So this will be blocked. And then you have A, B, and C bar. So A, B is here and C bar is here. So which means you're going to have 1 here. So you have like at 4 places you have 1. This, and that. So let's see. So plot once. So now we already know that how we have put these ones. We looked it into the Boolean expression, and based on that we have put 1 on these top in these spots, and rest of the places you can just put zeros if you want. And then the next important step after putting it into the table is grouping. Okay, so we're going to group once. Okay, so if you see these are 2 ones and these are 2 ones, so you can group them. So loop groups. So this is one of the rule in the K-map. So there are several rules and this is one of the rule. Okay, so in this first rule you can loop the groups. Okay, so right now we are looping only these twos. Okay, only when you have 2 ones in this form you can loop them. If you have like 1 here and then another 1 here, you cannot loop them. It has to be like that. If you have like 1 and 1 here, you could have looped that. And if you have like 1 here, then you could have looped actually whole 4, which is another rule. We'll come to that later on, but for now understand that we are right now looping only when you have 2 ones. Okay, so these 2 are closer, so this is forming a loop and this is forming a loop. make sure that you are not looping this with this one or this with this one. Okay, that's not possible. So once you loop, now what we should look here. So we see that what is common to this loop. C bar C, is it common? No, this is not common. If you see, A bar B bar is common, right? So to this loop, A bar B bar is common. So we will take this A bar B bar out, and that will be our first expression, or you can say half expression to make the full Boolean expression. And then if you see here, okay, so what common part you see? Let's start from the left hand side. So here I see the common part is A, and here A is there, and then here common is C bar. Okay, so what we can do, we can use A and C bar is going to be our next expression. So eliminate variables is a third step, and form simplified minterm expression. So you see, this was your A C bar. A is this common, and then C bar is that. A bar B bar is this common. Okay, so that's how you do it, and you simplify the expression. So this thing we simplified it for from the truth table also, and now we use another method, which is the K-map method. Okay, you might be thinking like, why do we need to do this? Like, why do we need to make the K-map if we can do use just one method? So my answer would be like, right now you're just dealing with 3 variables. Just imagine if you have like more variables, 4 variables or more than that. So in that situation, this K-map is like very helpful. And there are many rules in K-map which you can use and simplify the expression in like few minutes, right? Right now we just use only loop group rule. So this is one rule which we have used, and there are many rules in K-map which you can apply based on the complexity of your K-map, and then you can simplify the Boolean expression. Now let's see next. So simplify Boolean expression using the Karnaugh map. So now here, interesting is we have 4 variables. So we have 4 variables here, A, B, C, D. Previously we just had 3. So when you have the 4 variables, your K-map is going to look different. So AB portion, this is going to remain same. But here you previously just had C, so you had like C bar and C, but now since you have D, so you have to make combination for that too. Okay, so that's why you see here CD bar, C bar D, CD and CD bar. So if you mess with like how they are placed, like if you put CD here and C bar D, then your simplified expression is going to be incorrect. It's not going to be right. So you have to make sure that you put them in order. Okay, so this order is extremely important. Now the next step, what we are going to do is to just follow the Boolean expression and then put the ones based on what is mentioned over here. So we have like A bar, A B bar, C bar, D bar. So let's first see A B bar. So we have A B bar here, and then C bar, D bar. So we have C bar, D bar here. So we will put here 1. Okay, so that will be our first for this one. And then we have A, B, C bar, D bar. So AB is here, and then C bar, D bar is here. So which means this is going to be your 1. And then you have A bar, B bar, C, D. So which means A bar, B bar, C, D. C, D is here. So this is going to be your 1. And then you have A bar, B bar, C and D bar. So A bar, B bar and C, D bar is going to be here. So let's make it more clear by this. So this is what we discussed, right? Now we have for each of these, we have 1 in the K-map. Okay. Now by rule of loop grouping, okay, if you remember, if you do that, what will you get? So loop grouping we can do here, right? So we can loop this one, we can loop this one. Okay, so if you loop this one, let's see, if you loop this one, what is common? in this loop, this C bar D bar is common. So and if you see here, this A is also common. A and then C bar D bar is common. And here if you see, what is common? So you have common A bar B bar, and then among these two you have C common, right? Because D and D bar are different. So that is going to be your answer. So let's see. Loop groups. Eliminate variables. So yeah, so you saw like eliminate variables like B bar here, because that was like not common part, and here D bar was not common, so you have eliminated that, and then you have a simplified form, which is A C bar D bar, right? And plus A bar B bar C is equals to Y. So this is your actually min-term simplified Boolean expression. Min-term, you remember, is the sum of products. So these are the products and this is the sum. Now next we have, so developing a NAND logic diagram using min-term expression. So here you have min-term expression A bar B plus A B bar is equals to Y. Now we have to make the combinational logic circuit using NAND gates. So previously what we did, we used like AND and OR gate, but now we are going to use the NAND gate. So we will first start with AND and OR gate, and then we will develop a circuit for NAND gate. So if you look this expression carefully, you'll get to know that in this, the big picture says that this is the OR gate, right? And A bar B and A B bar are the inputs going into the OR gate, right? And then you have to make two AND gates, and to each AND gate there are two inputs. So first AND gate will have A bar B, and second AND gate will have A and B bar. Now you might think like, how we're gonna get B bar and A bar in the logic gates? So there are many ways you can get. So one of the way we'll be discussing here. So you saw this is our OR gate, which has A bar B and A B bar, which is and that is equal to your Y. So these are the two AND gates. So A is going in here, and then B is here. Okay, so some part of A is going into to this AND gate, but this A is like complemented. So that's why you have a NOT gate here, because if it goes through this will become A bar or A complement. So A complement will go into this AND gate, and then this B is going in here, and then similarly here that B is going through the NOT gate, so B here is going to be complemented. So B here, and then here it will be complemented. So B complement will go into the AND gate, and A will directly go into the AND gate, and then here they will form. So this will form A B bar, and this is going to form A bar B, and both are going into the OR gate. So that's how you form a simple AND OR logic diagram from the Boolean expression, and this is a min-term expression. Okay. Sometimes people use like inputs differently, not in this way, because right now we are dealing with like a very small or basic circuit. But if you have to draw, like maybe imagine like maybe 10 of these, right? So for that, just taking it through these A, B is going to be very difficult. So what we do, like in those cases, we just create the rail. So for example, I just say like here is A, and then create a whole line over here till down, and then I have like, let me just use this. So if I have like something like this, and then maybe like a gate here like this. So this is going to be my A, and this is going to be my A bar. And then you can just take the input and then put it into the gate, and then take the input from here, put it into wherever you want. So this is like just one example you can use for A, and then similarly you can use for create it for like B also. And they are usually, these rails are created like simultaneously. Now let's see how we can substitute the NAND gate for this logic, for this minterm expression. So substitute NAND gates for each inverter and an OR gate. So this circuit which you see here, this is also going to produce the same output which this circuit has produced. So you can take a pause at this point and see like how this is going to make the same expression as above. So how you're going to compare that? You have to feed in all the inputs. So for example, A is going here, and you have B going in here, and then other input is going in here, and same here, A is going in here. Okay, and you have to test it out, like what output you are getting out of these NAND gates, and how they are same as above. Okay. Now next important topic which we are going to see is the data selector. So, manufacturers of ICs, they have simplified the job of solving the simple combinational logic by producing these data selectors. And what this data selector do, it is often like in a one package solution you will find, which has like complicated logic circuit inside it, and this data selector help in picking up or selecting a particular input and then sending it to the output. So here you see 1 to 8 data selector, and this is the input which is having three variables and different combination of inputs it will have from 0 to 7. And then you notice that this is your three data selector input labeled A, B, and C at the bottom of the data selector, and then you have output of the data selector is labeled as W. So the basic job the data selector perform is basically transferring the data from a given data input 0 to 7 to the output. So which data input is selected is determined by which binary you place on the data selector input at the bottom. So if you have like 0 0 0, so this whatever the output is at this input will go in here. If you place 1 1 1, so whatever it will select this input, and whatever the output is there at this point, it will be sent out here. Okay, so if you think of data selector, you can think of it compared to like rotary switch. So like in a rotary switch, as the switch rotates, so each position has some selected value, and based on that some output is generated, and each has like separate or unique code, and each unique code represents some output. So similar to that, like data selector, they help in selecting the particular input, and based on that particular input the output is generated. Okay, so now let's see what is the output from the data select. So right now the data select we have is 1 0 1. So before we understand like what this 101 data select input means, we need to see here at the data input side, the sequence which you see 100101110, this is your Y. This is your output Y from some combinational logic circuit. You have some inputs and then you have some outputs. So this is like AND output which we have in this sequence, and these correspond to these place values 0 1 2 3 4 5 6 and 7. So now at 101 is at what place we have to determine. So you can use, if you directly remember, you can just go on and see like which number it is, or otherwise you can use that binary to decimal conversion. You can use that method. So if you remember the place values, like here it was 1 and here it was 2 and 4 and so on, 8 and 16. So here we have like 1 here and 1 here, so which means this is going to be your 5. This 101, the decimal conversion is going to be 5. So at 5, what number we have, like what binary number we have? So at 5 we have 1. So we have 1, which means this one is going to be sent to W. Okay, so at 101 we have 5, and at 5 we have 1, so 1 is going to be sent here. So either you can say 1 here, or you can say the output should be high. So both are the same thing. Let's see if our answer matches. So yes, here the output is high, which means 1. So similarly, for example, if you have CBA as like 111, then what will be your output? It's going to be 0, because at 7th place, when all these are high or all these are ones, at that point the output is 0. So here your output is going to be low. Now let's see for this case. So we have 0, 0, 1. Okay, so where do you think we can have 0, 0, 1? So we can have 0, 0, 1 at this place, because at this it is 0, 0, 0 and this is your 0, 0, 1. So at this place your output is 0. Okay, your input which is going into the data selector is 0 based on this data select input, and the same thing is going to appear at the output. So you are going to have a 0 or a low at the output. So let's see here. So we have low here. Output is our low, which is 0, and this matches also because we had a 0, 0, 1, so we selected this one. That's why you have 0 here. So that's how the data selector input works, and we will be using some of the ICs, data selector ICs into our experiments, and you will have a good idea like how it works. We have one more. So for 0, this is now going to be very simple. You know that at 0's position we have like high here, which is 1, so we have high. And let's see, so 111, so we have discussed this case already, so we have 0, so this is going to be low. Okay, now we have used the data selector to perform the logic described in the truth table. So again, this is the three variable 1 to 8 data selector. So let's see. So this is 1, this is your output Y, which is going in here, and then you have 0 here, you have 0 going into the 2's, and then 3, and then 0 to the 4, 1 to the 5, 1 to the 6, 0 to the 7. So you have all the outputs here going in to this input side of the data selector. Okay, now let's see if we have 0, 1, 1, then what will happen. So 0, 1, 1 is what case? 0, 1, 1 is this one, when this is C is 0, B is 1, A is 1. So at that point output is 1. So our output here W is going to select this one, and output is going to be high. Now let's see the next case. When you have 0, 0, 1, so at 0, 0, 1, so this is the place value 0, 0, 1, corresponding to that you have 0, and so the same 0 is going to be obtained at the output side when you have 0, 0, 1 data selected. So that's why you have low. Now let's see another case when you have 110. So 110, we have to look here. 110 is at this place, and at that point the output is high, which is 1. So the same is going to obtain at the output side for this particular case 110. So you're going to have 1, which means you're going to have high. So I hope by now you must be able to understand how this data selector thing work, and we will be doing more examples in the lab. So this is the end of the lecture. Thank you so much for watching.